Okay, so today we're going to talk about one-to-one functions and inverse functions. Basically, you have to talk about one-to-one functions because the only functions that also have inverses that are also functions are one-to-one functions. So we're going to talk a little bit about what it means to be one-to-one. So let's suppose that we have, the old traditional bubble graphs or whatever you want to call it. And let's say that we have, here's a state, and here's population. Okay, so you can say, let's say we have Indiana, let's say we have Washington, let's say we have South Dakota, let's say we have North Carolina, and let's say we have Oklahoma. Okay, and then it has 6.6 million, 7.1 million, 0.9 million, 9.9 million, and then 3.9 million. And then we're going to do mapping. We're going to map this to this. We're going to map this to this, this to this, so on and so on. Okay, so here's the thing. This is a function, right? But more than that, it is a one-to-one function. So not only does every term, not only does every domain value have only one answer, but they all go to their own respective answers. So a one-to-one function from your book says that a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range, that is x1 and x2. So basically saying that you will never get this situation. F of x1 will never equal f of x sub 2. That will never happen, okay? So that's what they're telling you, is that situation can never happen, that these two will not be equal ever. But basically, that's what this graph is trying to show you as well. So here's something that is still a function. Let's say we have 1, 2, 3, 4. Okay. And then let's say we have 5, 6, 7, 8. So in this case, let's say we have a mapping like this. Let's just do this. So let's say that 1 and 2 go to 5 and 3 and 4 go to 6. So this is still a function, right? Because, this is still a function because when you plug 3 in, you get 6. You don't get 6 or 5, you get 6. When you plug 4 in, you get 6. So it's still a function. So this is still a function, which is great. But it is not one-to-one. So this is how I'll write one-to-one in general. It's just easier to write it this way, okay? So it is not a one-to-one function. So we're really concerned with one-to-one functions in this particular section, okay? Now there's a way you can look at a function and tell if it's not one-to-one. So let's say we take our basic parabola, right? Y equals x squared, or f of x, f of x equals x squared. Now the thing is that this is a function because I can draw my vertical line anywhere I want, anywhere, right? Anywhere. And it will pass the vertical line test. So it passes vertical line test. However, it does not pass the horizontal line test, okay? However, f of x, does not pass the horizontal line test. Okay, so the horizontal line test we can use graphically to look at something and see if it would in fact be a one-to-one function, okay? Now, here's the thing. I could, however, draw a parabola I could say f of x equals x squared, and I could give it a domain restriction. I could say that the domain, we could say, is from 0 to infinity only. So normally the parabola would look like this, right? Okay. However, because we say that we only care about the parabola from 0 to infinity, we could erase that and we would only have this part of the parabola. So now, will this pass the horizontal line test? Sure. And will it also pass the vertical line test? Sure. So this is now f of x is a one-to-one function. So to be a function, it has to pass the vertical line test, but to be one-to-one, it has to pass the horizontal line test. Okay, so graphically, you can look at things like that pretty quickly. Okay. Now here, let me just make sure I'm doing okay on this. Okay. So the thing is we want to find inverse functions. Okay. So if you have a one-to-one function, then corresponding each of the x's in the domain of f to exactly one of the y's in the range of f, okay, and then corresponding each of the y's in the range of f, there's exactly one x in the domain. Again, that's basically saying that it's one-to-one. The correspondence from the range of f back to the domain is called the inverse. So you can work backwards, okay? So the notation we are going to use for notation for f inverse, or I'm sorry, let me write this. Notation for inverse functions is generally considered to be this, f inverse of x. So this means f inverse, all right? So when we take trig, we're gonna do something like where we'll say sine inverse of x. That doesn't mean to the -1 power. It actually means the arcsine or the inverse function, okay? So inverse functions are very important in mathematics. It's a way that you can undo a square with a square root. You can undo different functions with their inverses, okay? So the main thing is we have to check if something is one-to-one. If it's one-to-one, then it will have an inverse that is also a function, okay? So that's kind of what we're gonna stick to in this case. So let me look at the next part of this. So I think the big thing for us will be finding the inverse, okay? So finding the inverse is a big thing that we'll talk about, all right? So one of the things that you have to do, okay, is the first thing you have to do is you have to rewrite f of x and set it equal to y. Second thing you do is you interchange let's say swap every x with y and back. Okay, then solve for y. Then the last thing we will do is we will then replace y with f inverse, okay? So this is kind of our technique that we're gonna use, okay? Now, there'll be some consequences because of this, all right? So I wanna show you guys that. So suppose, I guess I might be going a little bit out of order according to your book. I teach it a little bit differently. Let me go back and let's just kind of talk about some of this stuff real quick, okay? So here's the thing. Because the x and y are swapped or interchanged, okay, that also means that the domain and ranges swap between f of x and f inverse, okay? So suppose that I gave you these points. Let's say that you had the point -3, -27. Say you also had the point -2, -8. Let's say you had the point -1, -1. Let's say you had the point 0, 0. Let's say you had the point 1, 1. Let's say you had the point 2, 8. And let's say you had the point 3, 27. Okay. So here's the thing. Let's say that this is a one-to-one. Oops. I say find the inverse of this one-to-one function. So it is one-to-one and it is a function because every mapping is, goes directly to itself. So what we could do is we could say, well, -3, -2, -1, 0, 1, and 2, oops, and then 3. So let's say this is our domain, right? That's our x's. And then let's say we have our ranges over here. So we have -27, -8, -1, 0, 1, 8, 27. And then we map. This maps to this, 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 and so on, okay? So again, it's obvious it's a one-to-one function, all right? Now here's the thing, this is the range, okay? So if you're going to do the inverse goes back the other way. The inverse says, well, -27 actually maps to this. -8 actually maps to this. This 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 maps to this. So this is f inverse, and this is f of x. Okay? So what that means is that if I want to find the domain, so finding the domain, let's do this. Let me say that it's this way. F of x has a domain, and this domain would be, and again, this is just a set of numbers. It's not an interval. It's just -3, -2, -1, 0, 1, 2, and 3. And that would be the domain of f of x, right? And now here's the range. The range would be -27, -8, -1, 0, 1, 8, 27. Okay, so that would be the range. So now what we would do is if we wanted to look at f inverse, okay, f inverse would have a domain and a range as well. However, f inverse domain would become -27, -8, -1, 0, 1, 8, and 27 because it's mapping backwards. And then this would become -3, -2, -1, 0, 1, 8, 27. So that is the relationship between the function and its inverse, okay? Is the domains and ranges interchange, right? Okay, so you see how the domain and the range of f of x became the range and the domain of f inverse, okay? So that's a consequence of the way inverses are built, or I shouldn't say a consequence, it's a result of how we think about them and what we call them, what they're actually doing, okay? So you flip-flop the domains and ranges, okay? So if this comes back to the previous section, if you take the composition of two inverses, okay? If you take the composition of f inverse of f of x, you will get x, if they are in fact inverses, where x is in the domain of f. So very similar to what I wrote for you guys in the previous section. And if we take f of f inverse of x, and we get x, we have where x is in the domain of f inverse. So whenever you take the composition of two functions and you get x, okay, coming from both directions, f inverse and then f of f inverse, when you do that and you get x, that means that this right here means that they are in fact inverses. So this is a way you can test. Or this is a way you can show that two things are inverses, is you can take the composition of these two functions, and if you get x as your answer from both ways, from f inverse of f and then from f of f inverse, if you get x from both directions, you have just shown that they are inverses of each other, okay? Another thing that we have to talk about, so let's verify this real quick. Instead of going on to the next thing, sorry about that, you guys, let's verify. So I want to verify that g of x equals x cubed is how did I write this? I think I wrote this wrong. So I want to verify that the inverse, how do I want to write this? No. Verify that the following are inverses. Okay, so I have f of x equals the cube root of x, and g of x equals x cubed, okay? So if we want to verify this, first we have to know, are these both one-to-one functions? Well, I know what a cube root looks like, right? A cube root takes on this shape, so that's going to be one-to-one. And we know that x cubed takes on this shape, right? So that's going to be one-to-one. So they're both one-to-one functions, okay? So now I want to see if they are in fact inverses of each other. So what I'm going to do is I'm going to find f of g of x, and I'm going to find g of f of x. So then when I do this, I'm going to take and I'm going to put f of x cubed into my f function, which would be the cube root of x cubed, which is in fact x, check. Now I'm going to do g of, and I'm going to put the cube root of x into my g function, which would be the cube root of x quantity cubed, and then that would be x, check. So yes, they are inverses. Okay, so they are in fact inverse functions. All right, so this is something that you guys can do. There's quite a few homework problems on this that will allow you to, kind of practice this technique. So now, at the end of this, I want to write down a few things that we kind of keep an eye on, but kind of the big deal about this is finding inverse. So I might say find the inverse of f of x equals, and I could say 2x plus 3, okay? So we go way back here. Like I said, I wrote it a little too early. We rewrite f of x as y. Then we interchange or swap out every x with y and then solve for y. So I'm going to come back here. I'm going to say y equals 2x plus 3. Then from here, I'm going to interchange the x's and the y's. So this becomes 2y plus 3. Now we're going to get x minus 3 equals 2y, and then we're going to solve. So we now have x minus 3 over 2 is equal to y. Now that's not quite the answer yet. We now know we have to flip back f of x and call it f inverse is worth x minus 3 over 2. So this is actually our f inverse. So what I want to do is I want to graph it on the calculator. And I want to show you guys another relationship that comes to pass, another way to recognize inverses. You know, it might be easier for me to use the calculator, the TI-84. Okay, so let's go from there. All right, so let's go y equals, and let's clear this. Let's clear this. So let's plug in the first one. And the first one was 2x plus 3, right? So let's graph this. So you guys see it's like that. Now let's graph the other one. And our inverse would in fact be, what did I get? X minus 3 over 2. Okay, so this would be x minus 3 divided by 2. Oops. So let's graph. Okay. Now you guys see I don't know if you can see the relationship, but let me do one more graph. This one is y equals x. So see that line that's in black? That is the line y equals x. The blue line is the original function, 2x plus 3, and the red line is the inverse function. As it turns out, in order for two things to be inverses of each other, they are reflections across that line, y equals x, across that black line. So you could literally fold your paper right over that and they would land on top of each other. Okay, so that's another thing that you notice about inverses, is that they are reflections across y equals x. And if they're not, then they're not inverses. They're something else, right? So this is a big deal for inverses. Okay, so we come back here. So we had this graph, you know, what did I say? Up 3 and then up 1, 2 and over 1. So we would have got this guy, something like that. You guys get the idea. And then we would have had this line right here goes through. Oops. You guys get that. And then this one would have been -3/2. So here's -1, -2. So -3/2 would have been there. And then we rise 1 and run 2. So we would have had this. So something like that. That's actually not bad. It worked out decent. So that's the thing. This is f inverse of x. And this is f of x. And this is y equals x. So this line, y equals x, is for all inverses. That's what they reflect across. Now remember, why is that the case? Because think about this. You interchange the x's and the y's. So there's now a relationship between y equals x, okay? So that's why they're always reflections. And that's something that you can do when you're looking at the domain of the f function and you get the range. Well, then you can take the range of that, and that's actually the x value for the inverse. It's kind of crazy how it works. But you'll get more practice from it in the homework, okay? So let me give you guys one more. Let's see here if I have another one. Okay, yeah, whoa, this one looks pretty bad. Okay, let me see if I want to do this one. Okay, so let's try this one. So find the inverse. So let's say that we have f of x equals x over 2x plus 1. I have a bad feeling about this. Okay, so first things first is we say y equals x over 2x plus 1. Okay, and then the second step says that you interchange the x's and the y's. So now this is going to become x and this is going to become y over 2y plus 1, right? We flip-flopped. Now that we have this, our job is to now solve for y. But the only way to solve for y is to get y out of the denominator. So I'm going to multiply 2y plus 1 over to the other side. Oops. And that'll cancel, but now I got to put a 2y plus 1 over here. So now this will be x times 2y plus 1. So this will be 2xy plus x equals y. Now, whenever you are trying to solve for a variable and it's on two separate sides, you have to get it on the same side so you can factor. So I'm going to now subtract minus 2xy minus 2xy. So now I have x equals y minus 2xy. But now there's a y in both of these. So now I can factor out the y. And this becomes y times 1 minus 2x. And now finally, I can divide 1 minus 2x over to the other side. Okay, so let's come up here. And this will be y equals, sorry about that, y equals x over 1 minus 2x. Okay, so now that we have this, we remember the last step is to now call this f inverse of x equals x over 1 minus 2x. Okay, so that would be our inverse function. We did our job. So this is good practice, especially manipulating fractions like this and factoring. These are very common problems that arise with inverse functions. So I just wanted to make sure you guys did that. So in summary, okay, so inverses. Okay, so what's the first thing we know? Well, let's just start writing down facts. Inverse functions reflect graphically across the line y equals x. Okay. Another thing we know is that f of f inverse of x equals f inverse of f of x. Okay, so we know that. So basically, when you take a function and you compose it with its inverse, you better get x. So that's kind of the big takeaway from that. So that's a way to verify. Okay, so another thing we know, another thing we know is that inverse functions, or no, how about this? This is a better way to say it. Only one-to-one functions have inverses that are functions. Okay, let's see, is there any other fact we know? Let me see, only one-to-one functions have inverses. Ooh, that's pretty ugly. Another fact, we know that the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. Okay, so basically that the domain and range is flip-flop for f and f inverse. So this is quite a few little things about inverse functions. Inverse functions are really, you've already been using them a lot. Whenever you cancel out a square root with a square or something like that, you've been using inverse functions in a way. You've been using compositions of functions also before, even before the previous video. So this is just some stuff about inverses. There's quite a bit of homework for these sections, so I really want you to get started on these. So I'm going to post these videos and go ahead and give these a shot, you guys. Okay? Thanks for watching.